Chapter 2.6, Related Rates, Day 1. Today we're going to look at one of the more difficult topics in Calculus 1, and that is related rates. It is also a topic that they cover quite heavily on the AP exam, so it is very important to take your time and understand this. Related rates is an application problem, right? We'll be doing a lot of story problems in this section. And it has emphasis on implicit differentiation. We'll first talk about how you do related rates problems, and then we're going to work through a couple examples. Basically, there's 4 steps to doing related rates problems. Your first step is to identify what you know and what you don't know. Sometimes it is helpful to draw a picture. The second step for related rates is to write an equation that involves the variables that you're looking for and you know. Step 3 is to derive the equation with respect to time. And the final step is to substitute what you know into the equation and solve for what you don't know. It's not a lot of steps, but it takes a lot of thinking. So we'll start with the first problem. In the first problem, a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. And I did not include the figure because I want you to draw it. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? So we'll draw a pond with the circles drawing out from the center where the rock was dropped. All right? Write down what we know and what we don't know. Well, first off, we know the radius is increasing at a constant rate of 1 foot per second. What that means is that the change of the radius with respect to time is 1 foot per second. So dr dt is 1 foot per second. When the radius is 4 feet, that means at a certain point in time, r is 4. What is the total, at what rate is the total area of the disturbed water changing? All right? That means we're looking for the change in area with respect to time. We don't know it at this point. All right? So now what we want to do is we want to write an equation. If we look at the information, we have circles, we have area, we have radius. What equation relates area and radius of circles? Area equals pi r squared. So now we have our equation, we have our picture, we have our unknown information, we have our known information. We want to go to step 3, and that is to take the derivative of our equation. Using the chain rule and implicit differentiation, the derivative of area is dA dt equals, derivative of pi r squared is 2 pi r, and then because we're with respect to time, we need dr dt. So now what we do, we have taken the derivative, that's step 3. We're going to plug in what we know and solve for what we're looking for. We don't know dA dt, that's what we're looking for. So I'm going to leave that alone. It'll be dA dt equals 2 times pi times r, which at this point in time is 4, times dr dt, which is 1. So the change in area with respect to time is 8 pi square feet per second. All right, that is a related rates problem. You're going to draw your picture, what you know, what you don't know. That's all right here. Draw your picture, state what you know and what you don't know. Write your equation involving what you know and what you don't know. Take your derivative and then do a plug and chug with the information you have so that you can solve for what you're looking for. All right, let's look at another problem. Air is being pumped into a spherical balloon. See figure 2.33. Again, I did not include the figure. At a rate of 4.5 cubic inches per minute, find the rate of change of the radius when the radius is 2 inches. So we will draw this picture out. We have a balloon that is being pumped up. And it is a spherical balloon, as spherical as balloons can get. Air is going into the balloon. All right? When we say it's being pumped up at a rate of 4.5 cubic inches per minute, that is how fast the volume of the balloon is expanding. So we would say dV dt, the change of volume with respect to time, is 4.5 cubic inches per minute. Find the rate of change of the radius. So that is dr dt. We don't know it. That's what we're looking for. When the radius is 2 inches. So at the point in time when the radius is 2 inches, we want to know how fast is it growing. Our equation relating volume and radius of a sphere, well, that would be volume equals 4/3 pi r cubed. Now we've got step 1, our picture, our knowns and unknowns. We've got step 2, our equation. Now we're going to take the derivative of our equation. The derivative of volume with respect to time is dV dt equals 4/3 pi r cubed. Applying the chain rule becomes 4 pi r squared times dr dt. So plugging in what we know, 4.5 equals 4 pi r squared is 2 squared, which is 4, dr dt. And so now to solve for dr dt, we're going to divide both sides by 4 pi times 4. Our change in radius with respect to time is 4.5 divided by 16 pi inches per minute. Okay. So in review, the steps for a related rate problem. There are 4 of them. First, list what you know and don't know. If necessary, provide a sketch so you can visualize it better. You're going to write an equation. Make sure you look at what you know and don't know when you write your equation, so your equation can involve those variables. Step 3, take the derivative of both sides with respect to t. Do it implicitly using the chain rule. And finally, once you have your derivative, plug and chug. Substitute what you know in, solve for what you don't know.